Hello everyone. So in the last class, we discussed the closure problem in detail and we looked at how we could split the Reynolds stress term into an isotropic part and an anisotropic part. And the isotropic part, we absorbed it into the pressure naturally because the pressure is also the isotropic stress component of the overall stress tensor. So we absorbed the isotropic part, which happens to be the kinetic energy, right? The diagonal components of the Reynolds stress term, which is u1 squared mean plus u2 squared mean plus u3 squared mean. And so it could be written as the kinetic energy term, which was absorbed into the pressure. And then the only thing that actually mattered, that was creating the additional effect in turbulent flow, was the anisotropic part of the tensor. Otherwise, the isotropic part or the turbulent kinetic energy is all it is doing is it is increasing the overall mean pressure. That's all it is doing. So the anisotropy was what mattered. So we'll see a similar concept here when we discuss the irrotational motion. So as you know, turbulent flows are rotational. It cannot be irrotational. But let's consider irrotational flows for a minute here. Now here, if the flow is irrotational, the vorticity is going to be 0 because rotation is 0. So the mean vorticity, the fluctuating vorticity, everything is going to be 0. Which means the vorticity which is defined like this, one component of the vorticity, which is del ui del xj minus del uj del xi. Now there will be a constant multiplied by it, but if you take a cross product of the velocity, like omega is basically del cross u, isn't it? So if you actually work it out, one of the components is going to look like this, del ui del xj minus del uj del xi. This is also going to be 0. Which means if you take ui times that vorticity, okay? If you take ui times that vorticity, del ui del xj minus del ui del uj del xi, mean of that is also going to be 0 in irrotational flows. Here, if I multiply this out, ui times del ui del xj, let's say I do that, then I can write this as half ui ui, because this del ui times del ui del xj, I can take the ui inside the derivative, and then if I just put a half there, that would tell me that I can write this as, so if I just take a derivative of ui over 2, that would be the same as ui times del ui over del xj. And so all I'm doing is I'm taking the ui inside this derivative. That is all I'm doing, and I write it in this form. Then the second term, which is ui times del uj del xi. Now that too, I can take the ui into the derivative. There will be this additional term which goes to 0 because of continuity, and that is how you get del xi of ui uj, the Reynolds stress, isn't it? And now what we know is that since this is equal to 0, this part is also equal to 0 in irrotational flows. So what we are saying is half ui, which is the sum of the diagonal components in the Reynolds stress tensor, and then ui uj, which is again going to be the anisotropic part, isn't it? So del xi of ui uj. So now if I write, so this is going to be equal to 0, which means I can write this equation as del xi of ui uj is del k del xj for irrotational flow. What I have is the Reynolds stress tensor, and del xi of that is equal to the derivative of the kinetic energy with respect to j. This is the Corson-Kitzler equation. This is applicable only to irrotational flows. Now, what does this mean? Why did we do all this? We considered irrotational flow and we equated the vorticity to 0, and from vorticity we derived it in terms of the Reynolds stress and the kinetic energy. Why did we do this? So interesting thing is you get something that is very similar to what we saw in the last class, where we could absorb the isotropic part into the pressure. So here the Reynolds stress has the same effect as the isotropic stress. So what is happening here is what you're saying through this equation is that the Reynolds stress, of course there is a derivative there, the derivative of the Reynolds stress is the same as the derivative of the kinetic energy. The kinetic energy we know is the isotropic part of the Reynolds stress tensor. And what we are saying is that the Reynolds stress has that same effect. So essentially, the Reynolds stress in irrotational flows is having the same effect as what kinetic energy would be, is basically only having an isotropic effect. It is not having an anisotropic effect like you would have in rotational flows, which is what turbulent flows are. So that is what we mean by this. The Reynolds stress has the same effect as the isotropic stress, which can now be absorbed into the modified pressure. So that means if I now have a modified mean pressure, for example, I would have to take into account the regular pressure, the kinetic energy, and the Reynolds stress in there, because that is all the Reynolds stress is doing. And we know for sure that that is absolutely not true in reality. Reynolds stress contributes towards the anisotropy, whereas according to these equations, it is only contributing towards the isotropy. All the more proof that turbulent flows are rotational. They are not irrotational. They are rotational flows. There is always vorticity in turbulence. There is rotation in turbulence. This component is not going to be zero. It is going to be non-zero. This is not going to be true. The Reynolds stress has an anisotropic effect. But the interesting thing is, in irrotational flows, that is all the Reynolds stress is doing. It is just bumping up the pressure, bumping up or bumping down. But it is doing is it is affecting the mean pressure. That is all it is doing. That's the interesting conclusion here. Moving on, let's talk a little bit about symmetries. So for some flows, this symmetries in the flow come about because of the geometry that we have. I mean, we saw earlier where we had a channel flow where we assumed certain directions to be negligible, the gradients in certain directions to be negligible. And that's kind of what we are discussing here. So if you consider a statistically 2D flow in which the statistics are independent of one of the directions, say x3, and also which it is, let's say it is statistically invariant to any reflections of the x3 coordinate axis, in which case the PDF, okay, since we are talking about statistics, we'll just take PDF, so that way all statistics come under that umbrella, and then you would have del f del x3 is equal to 0 because all statistics are invariant in the x3 direction, which means and also they are invariant to any reflections in the x3 direction. So that means f of v1, v2, v3 is the same as f of v1, v2 minus v3 because they are invariant to reflections. This means the mean across u3 or the mean of the u3 component is going to be 0. u1, u3 fluctuating, as in the Reynolds stress term u1, u3 is going to be 0, and u2, u3 is also going to be 0 because anything related to u3 is going to be 0. So in that sense, the Reynolds stress term is going to boil down to this. You have multiple zeros here, and u3 squared will be there because the kinetic energy is there, but the mean u3 is going to be equal to 0. So that is what you have in a statistically 2D flow. So because of the symmetry, you have now simplified the problem significantly. Now, in addition to being statistically 2D, let's say you had the turbulent channel flow that you had earlier, then it is statistically symmetric about x2 as well. So then the symmetry implies that f of v1, v2, v3 is also f of v1 minus v2, v3, and then from which we can conclude that u2 mean is equal to 0 and u1, u2 is equal to 0 are odd functions of x2. So then all you have is u1 squared, u2 squared, and u3 squared. So this is what happens when you make significant assumptions, and because of this you're utilizing the symmetry of the stress tensor. So that's one point. Now let's go to the mean scalar equation. So when we discussed all the governing equations, we discussed the continuity, the momentum, and the Poisson, which is derived by taking the divergence of the momentum. But we also discussed the scalar equation. So naturally, let's take a mean of the scalar equation. So just like the Reynolds decomposition is applied to the velocity, where you have the velocity being decomposed into mean and fluctuation, the scalar can also be decomposed into mean and fluctuation, and that is what is done here. So phi prime is phi minus phi mean. Now this is the scalar equation, which is the unsteady term, the convection term, or advection I should say, and the diffusion term. So del dot u phi equals gamma del squared phi. Gamma is the mass diffusivity, thermal diffusivity, depending on what you're considering as the scalar. Now what we do is we take an average of these equations, right? We decompose it into mean and fluctuation, and then we take the average, just like we did for the momentum equation. I'm not going to repeat the procedure here, but really the only complication is related to this nonlinear term, which is what we'll do, right? So u mean plus u is phi mean plus phi prime, and then you would all the components except for these two multiplied together and these two multiplied together will retain. Every other term would go to 0 because the mean of u fluctuation is equal to 0 and the mean of phi fluctuation is equal to 0. Isn't it? By the same token, the mean of the phi fluctuation is going to be equal to 0. So you are down to these two terms as far as the nonlinear term is concerned. Now you put that into the mean scalar equation, then you have d phi dt plus del dot u mean u times phi, and this is coming from the nonlinear term, right? And then you have the viscous term here. Now I'll use the mean substantial derivative definition. This can be as you know, this can be split into two by just using the chain rule. So then I can write it as mean substantial derivative is del dot gamma del phi minus u phi prime. U phi prime, which is coming from here, and this is the same as this term here. So the Laplacian is written as divergence of the gradient. That's all. The Laplacian is written as the divergence of the gradient here. This is coming from this term here, and everything else gets bulked up into the mean substantial derivative. So as we saw in the Reynolds equations, the Reynolds stress term was this additional term that was popping up when you have a turbulent flow. Here you have a scalar flux, a turbulent scalar flux term that pops up when you have when you do an averaging in a turbulent flow. Again, like we had the closure problem for Reynolds equations, we also have a closure problem here, because you know the u mean is coming from the Reynolds equation. The phi mean is coming from this equation. What do you do for u phi prime? So you will need a model for that. You will need an additional equation for that. Somehow that is your closure problem here as far as the scalar is concerned. This applies to when you're dealing with, say, temperature. This would be a temperature equation. Your scalar could be temperature and gamma would be the thermal diffusivity. So I hope that is clear. So the reason why we discussed the mean scalar equation is also so that we can discuss one of the most important hypotheses in turbulent flows, which is the gradient diffusion hypothesis. Most of the turbulence models, and again I'm talking about turbulence models, I am not talking about solving the Navier-Stokes equations exactly like you would do for a direct numerical simulation. Every turbulence model, almost every turbulence model utilizes this gradient diffusion hypothesis. So it started as a basis for a lot of simplified models, but now it is being used for a lot of turbulence models as well. So the scalar flux u phi prime gives both the direction and magnitude of the turbulent transport of the conserved scalar. And according to this hypothesis, what the hypothesis states that this transport is the negative of the gradient of the mean of the scalar. The scalar flux is the negative of the gradient of the mean of the scalar. So what we are saying is, and we've discussed this briefly when we talked about the discussion in Tennekes and Lumley's book, u phi prime mean is minus gamma sub t, minus gamma t, indicating that it is a turbulent diffusivity, not the same thermal diffusivity that we had earlier. It is a turbulent diffusivity, meaning it is a flow property, not a molecular property, not a fluid property, a flow property. So turbulent diffusivity times the gradient of the scalar. Now what you do is, if you replace this with turbulent diffusivity times del phi mean, by the way, put that in here, and this was negative, right? Then you combine your thermal diffusivity, or let's just call it diffusivity, and turbulent diffusivity together into one big effective diffusivity. You can write your mean scalar equation in this form. Mean substantial derivative is del dot gamma effective del phi. This, compare it to your regular scalar equation. d phi dt is del dot gamma del phi. It is exactly the same, except this was molecular. This is molecular plus turbulent, isn't it? Because it is gamma plus gamma turbulent. So there's a difference there. What we are saying is, you have enhanced the mixing. This is what we were always saying. The enhanced diffusion comes from this additional turbulent diffusivity that is built in there. Whether you can do that or not, we have already discussed that. This is actually not true. Turbulence is a flow property, is a property of the flow, not a fluid property, which means how can you write it as some new turbulent diffusivity? This is the apparent diffusivity that comes in. So that is why it is a hypothesis. The hypothesis is that it is proportional to the mean of the scalar. If it is proportional to the mean of the scalar, there is possibly a coefficient that governs the transport of that mean. That is why the hypothesis states that why don't we just write it as a turbulent diffusivity, just like we wrote it for laminar flow as shown here. Now you have it in terms of a new diffusivity. So that's what we mean. The derived equation is similar to the conservation equation for phi, except now you have replaced u with u mean, you have replaced phi with phi mean, and you have replaced gamma with gamma effective. I hope that is clear. So that takes us to the turbulent viscosity hypothesis. So we had the gradient diffusion hypothesis for the scalar equation. Now we are going to apply it, take the turbulent viscosity hypothesis. Again, the basis of a lot of turbulence models. This was introduced by Bissonnette, and we discussed this when we were discussing the history of turbulence. This was introduced by Bissonnette in 1877. It is mathematically analogous to the rate of strain stress strain relationship for a Newtonian fluid, where tau is equal to mu du dy. So Bissonnette said, if the molecular stress, the viscous stress, can be equated to the strain rate, why don't we have a turbulent flow where the turbulent stress can be proportional to the mean strain rate, just like we had for the gradient diffusion hypothesis. So in that sense, according to the hypothesis, if we write the deviatoric stress, which is minus rho ui uj plus 2/3 k delta ij, why don't we write that as proportional to the mean strain rate? So then I have minus rho ui uj plus 2/3 k delta ij is rho nu t. Then I have the strain rate del xj of ui, del xi of uj, obviously the mean of that, and that this is half of the strain rate, half Sij of the mean strain rate, of course. So that's how I write it as 2 rho nu t Sij. I'm sorry, there is no half. For now, we are ignoring the half and we are just considering it to be just Sij. So what I would have is this part here. There is a 2 here, okay, indicating that Sij is half of del xj ui plus del xi of uj. So if you define the strain rate like that, this term in the bracket here is 2 Sij. That's how we get the 2 here. So 2 rho nu t Sij. So nu t is your turbulent viscosity or the eddy viscosity. What we are saying is the deviatoric stress tensor, deviatoric stress term, which is minus rho ui uj plus 2/3 rho k delta ij. This is the entire Reynolds stress term. That is why you have the 2/3 rho k delta ij, because this is the isotropic part and this is the anisotropic part. That is equal to 2 rho nu t Sij. So that is the turbulent viscosity hypothesis. Once you do that, you can write nu t, you can lump that into your new term, which also had something that is very similar to the one that is shown in here in the bracket, in which case you will have the mean substantial derivative on the left hand side, which you always did, and then you could write this as nu effective, because this is now nu plus nu t times this strain rate. This right here is 2 Sij mean. And then you had the minus 1 over rho del xj of p plus 2/3 rho k. You see what I did here, right? When I split the Reynolds stress term into isotropic and anisotropic part, I combined the isotropic part of the Reynolds stress tensor into the pressure term, and I have the modified pressure. So I have this additional 2/3 rho k, and what I said was that is why the 2/3 rho k is built in here, along with minus rho ui uj. So essentially the ui uj is proportional to the mean strain rate. But because there is this 2/3 rho k that I have built into the pressure, I am expressing this part with a 2/3 rho k here. I hope that is clear. And so I have nu effective, which is nu plus nu t. That becomes the effective viscosity, just like you would have it for the diffusivity. So now instead of so this equation, again, just like we did for, let's compare this to the mean, let's compare this to the Reynolds equations, just like you had it for, you did it for the scalar equation. The derived equation is similar to the Navier-Stokes equations, except u is replaced with u mean, nu is replaced with nu effective, and this is replaced with the modified mean pressure. The 2/3 rho k here gets cancelled out with the rho k that you had put in here, okay? The 2/3 rho k gets cancelled out with that. So essentially you just have the Reynolds stress term, which is what you had in the Reynolds equations. It is just a manipulation of the terms here and there. So now, what does this mean, right? What we are trying to say is the gradient diffusion hypothesis implies that the scalar flux vector is aligned with the mean scalar gradient vector. That is what we are saying. The scalar flux is aligned, because what we said is the scalar flux u phi prime is aligned. So let me just say proportional to mean, isn't it? Is aligned with the mean scalar gradient vector. From a turbulence viscosity perspective, what we are saying is the anisotropic part. See, The anisotropic part ui uj minus 2/3 k delta ij. That is what you add here. This is the anisotropic part. Aij, we expressed it as an anisotropic tensor. That anisotropic part is proportional to the mean strain rate. So being symmetric and deviatoric, the phi components of Aij and Sij are related through each other through nu t. That is what we are trying to say. This is what it means. The scalar flux vector is aligned with the mean scalar gradient vector. And the anisotropic tensor, because now you have multiple components, it becomes a tensor. The anisotropic tensor is related to the mean strain rate, all through either through the turbulent diffusivity or through the turbulent viscosity. So for 2D, if you consider what this means for 2D boundary layer equations, only one component of the scalar flux and Reynolds stress appear in the equations because it's 2D and it's boundary layer, so you have neglected certain terms. So you're essentially what it boils down to is u2 phi prime is minus gamma, which is minus gamma t times del x2 of phi. This is what it means. And your covariance u1 u2 is minus nu t del x2 of u1. So a single covariance is related to a single gradient and also the opposite sign. Don't forget about the opposite sign. So the scalar flux is negative and u1 u2 is also negative. So if you have a way to specify gamma t and nu t, your problem is solved. Your closure problem is solved. If you have a way to specify what gamma t and nu t is, because the mean is known. The mean is known from the governing equations. The Reynolds equations gives you u1 mean, and the mean scalar equation gives you phi mean. So the only unknown is gamma t and nu t. If you have a way to figure that out, then your problem is solved. This is where the turbulence model comes in. Every turbulence model has a different way of specifying how you calculate nu t and gamma t. Once you calculate that, once you derive that, then you can solve for this. Now, at high Reynolds numbers and remote from the walls, these are found to scale with the velocity of the flow. And they are independent of the properties. They are independent of the molecular properties like kinematic, viscosity, and gamma. So the ratios both increase linearly with Reynolds number. And because molecular transport is negligible, they increase linearly. They are much higher at higher Reynolds numbers. So if you think about what the turbulent Prandtl number is, it is nu t over gamma t, which is found to be approximately 1. So if you can specify nu t and gamma t, then you solve the closure problem. And you can solve for u mean. You can solve for phi mean. And that's what I'm trying to say here. So what we have done is we've taken the Reynolds equations or the mean scalar equation. We have expressed it in terms of this new coefficient of viscosity, right? I mean, it is a flow property. It is a turbulent flow property. So that is why it is a turbulent viscosity or a turbulent diffusivity. It is a hypothesis coming from the gradient diffusion hypothesis or the turbulent viscosity hypothesis. We are saying that it is proportional to the mean scalar gradient, and the coefficient of the constant of proportionality is possibly a turbulent viscosity, possibly a turbulent diffusivity. We know that there is actually data that contradicts this hypothesis. However, this is the simplest way to actually move forward and solve the problem. It is the simplest way to actually have the closure problem solved. And this helps you solve for u mean and phi mean. So that's the end of this module. Thank you.